Do you have any questions? Wonder how is one of those questions I can show you the solution. If you did all your homework already on paper, we will add you extra credit later. I just finished reading this morning the extra credit for homework yet.
Go over number 6.
Okay. Can I call for this question? Over the passport question number 6. This is quite finding the mass of a function. If you try to find the mass function, you'll be integrating the density function. So we have the triple integral here. The x is from 0 to 4. The y is from 0 to 2. The z is from 0 to 5. At least this version, I've changed the number around. Z times e to the x plus 2y. Let me try to explain this question. Okay, we have to follow the integration order as intended. The z is 0 to 5, so it will be dz. The y is 0 to 2, so that will be the y. The x is 0 to 4, so that's the x. Kind of match. Kind of a princess kind of thing. So this is the order of the integration based on the integration limit. So we will integrate the inner layer of the integration is dz. So this is pretty much a coefficient for it. Let me try to follow the routine instead of using my own habit. Traditionally, we will finish writing all the integration notation. We're integrating the inner layers. Essentially, we're doing dz, z, dz. So if you integration the z variable, you have e squared over 2. The e to the x plus 2y is essentially coefficient. And here our upper limit and lower limit would be if you have z equal to 0 and z equal to 5. The upper limit and lower limit is really z value. On the other side, we have to finish up with dy, dx, and the appropriate integration limit is 0 to 2 and 0 to 4. This time I'm taking the time and write down the integration limit for the outer layer as well. We finish the integration on the z variable this much. So if we finish the calculation, is 25 over 2 minus 0 over 2. So that value is really a number. You bring that number over to the outside, it would be 25 over 2. And then we finish the rest of the integration. This is an indication that we should be able to separate the variable. So we have 0 to 4 and 0 to 2. And here we can separate them into multiplication, exponential function, summation in the exponent is multiplication of the exponential function. So it's e to the x, e to the 2y, dy, and dx. The second layer of integration is integrating. For instance, I intend to keep the notation, maybe at least we copy notation. We were supposed to integrate this part. We integrated the antiderivative according to chain rule is e to the 2y over 2. So this will be the antiderivative. try to make it visible. So you get e to the 2y over 2. That's the antiderivative of e to the 2y. And upper limit lower limit is y equal to 0 and y equal to 2. For this, you should remove your integration limits to evaluate the antiderivative. So that's the calculation involved in the y variable. And we put in the y variable value, it will be e to the power 4 over 2 minus e to the 0 over 2. So that's really a calculation. We should be able to pull that calculation number outside. So it's e to the power over 2 minus 1 over 2. And then we have last integration. That is integration 0 to e to the x dx. In this antiderivative is e to the x itself. You evaluate e to the x at 4 and at 0, which gives you 25, 2. And you can bring the 1/2 outside. And that will be e to the 4 minus 1. And then here you're going to have e to the 4 minus 1. Because the limit is 4, x equal to 4 and x equal to 0. So ultimately, these are identical. So you're going to have 25 over 4 multiplied by e to the 4 minus 1 squared. After that, you can use your calculator or you can leave it that way. That's the entire calculation for number 6. This is a calculation math that we're integrating. So essentially, it's a triple integral. Does that answer your question? Right. So if you have another version of the question 6, you might have different integration limit. This one is tricky. The board to causes us to have a 2 version of this. So if you have a different version, this multiplication might not be multiplied. You might have e to 1 power minus 1, e to another power minus 1. So then you might not have the square part. You should have this thing. So even if you have a different version of the same question, but it's very similar to this version. Yes. Oh, can you do 7? 7 of let me see your version. So maybe 2 different versions. Number 7 test 4. So you leave it that there and then see. So number 7 is a spherical coordinate calculation. Okay, so this is question 7. We were supposed to integrate this function. The function we're integrating is already in spherical coordinate at rho b theta equal to cosine b. If you have another version, you'll be integrating sine b. So pretty much similar, except the function is either sine b or cosine b. This one you have an integration limit that was 0 to 2.5 for theta and 0 to pi over 4. You have another version, it will be pi over 3, but this one is pi over 4. And then the value for the radius is 2 to 7. So we're integrating cosine b. But here it says use a spherical coordinate to integrate it. So our integration, the dv, right? The dv is not going to be dv. Since you use spherical coordinate, you have to have that change of variable is rho square sine b. No matter which version are you doing the spherical coordinate, you have to have the rho square sine b, and then d rho d theta. So that would be what we're calculating. Kind of like this question 6, the integration limit is all numbers. So we don't function in the integration limit. And make sure they match. Those for theta, that was for b, and then 2 to 7 is supposed to be rho. So the integration has to be in the right. These are all multiplication, cosine b times rho squared times sine b. They're multiplications, so we are able to multiply them separately. Like a times b, b times a, same, bring them outside or inside integration. So eventually the integration can be separated. So the theta is 0 to 2 pi. And in the integration function, there's no theta. So no matter how you do it, the inner layer will be a single number. When you're done, that's the number when you finish calculation number. So this number can be written out. So essentially you're doing 0 to 2 pi theta. So that means the theta can be separated from the rest of the integration. Also that if you integrate the d rho, it will be d rho square and then calculate 0 to 2 to 7. And then after you're done, that's the number that you can bring out of the integration. So then you can do it separately actually. So 2 to 7, we have rho squared d rho, which is integrated after you finish the integration of the number. The b phi of the integration of their phi is 2 times 4. This version is cosine phi, sine phi, which we have to use a substitution method to integrate. The other version may end up having sine square phi. You have to use a power reduction function to rewrite it. But either way, there are trig integration involved. It's not identical. If you calculate the first integration, you're getting 2 times. If you get calculating this integration, it will square integrated as rho cube over 3. So it's going to be 7 cube over 3 minus 2 cube over 3. And you gotta look at what that number is supposed to be. This is after you integrated the u equals sine phi, du is cosine phi, is d phi. So there is u du. If you integrate u du, it's u squared over 2. So the integral 2 is sine phi squared over 2. And we put in that limit phi equal to 0 and phi equal to pi over 4. If phi equal to pi over 4, sine pi over equal to root over 2. 2 over 2. That squared is actually 1/2. 1/2 of 2. So this calculation is possible. So everything combined, the final answer is 2 pi over 2. Pi over 2 times. Over here it would be 7 to the power 3. So 7 to the power 3 minus 2 to the power 3 will give us 335. So it will be 335 over 3. Yeah, that's pretty much. So 335 over 335 pi over 6. That would be it. Any questions? So this is one version of the question 7. It's a spherical coordinate with a triple. 2-dimension, we have rectangular coordinate and polar coordinate. In 3-dimension, we have rectangular coordinate, cylindrical coordinate, and spherical. Kind of have to look at the version of the system, depending on whether it's 1-dimension, 2-dimension, or 3-dimension. Any question? Right, I was going over the test board and handouts. If you're in the class, I can hand you over the exam, but if you're not in the class, you can let me know next time when you're in class, I'll take it out of my folder. I'm not sure I have graded. Yeah.
I think it was only you just.
You already saw it?
Yes.
This one?
Yeah.
I see. Let me do some calculation. I calculated the grade right before class.
Yeah.
So I was walking over, see who's in the class. If you're in the class, and I'll find the grade. If it's your name class, then they're probably going to see. Is it? And I graded question by question, so they're separate. Before I was looking at that. You can check it out every question. If you have any question for the individual grading, let me know.
Take
This exam really take me quite a while to finish the grading because there are really several different versions of every question. And there's not unique correct answer to a question. So I have to apologize for the time. And last Thursday we had exam. It took me a whole week to finish. I did a one question one day, and then something comes out and did another two question another day. So every day I did it question by question, so it will be fair for each student. I graded the same way, so that way I won't forget what was my role, what was the partial credit I was trying to calculate. All right, so this is today's attendance question on the board. But if you are in the classroom, I will try to combine all your questions total number and hand it back to you. If you're not in the classroom, you may see your grade on Georgia View shown after the class, because I was grading right before the class. That's why I find out the time is a little bit tight there. But it's definitely a problem adding the numbers up. So if you're on campus, see me after class today, you get to see your test paper. All right, that's for test 4. Feel free to mention any issues or concerns. We'll definitely talk about test 4 more on Monday if you're in class. All right, so basically test 4 going over one question per section out of the chapters 13. Most of them are integration technique. So if you're a little bit rusty on your calculation skill on integration, you may see a few points off here and there. But if you've been doing your homework, you can see the question that we have asked are really the homework question we did. So you're behind on homework and you probably can't feel the pressure. All right, on the board, we have a question that we will be doing for today's attendance question. It is a surface integral. We are going to use, the divergence theorem to calculate this. And this is one of the questions that I copied off of the textbook. So instead of ds, we have a d sigma, but it's the same flux calculations, calculating the flux F dot n ds. The surface is the solid bounded by the surface x squared plus z squared equal 4. Y equal 1, y equal 0. So it's a cylinder. I mean, you see x squared plus z squared equal 4. It's a radius 2 cylinder in the xz plane. And then y is the upper bound, lower bound, upper circle, and lower circle of the cylinder. So then those are the surface of the cylinder. So S is the cylinder of the solid region. Therefore, the evaluation of the evaluation is a closed surface integral. So we would be able to calculate its flux using the divergence theorem. So let's practice. I don't know if you remember the divergence theorem that we were talking about. It is a way of calculating surface integral in a slightly faster way, considering the version of the divergence value. Yeah, too large. So the calculation will be according to the divergence theorem. This flux calculation is equal to, maybe slightly small. Right, according to divergence theorem, this is equal to, running on the formula, this is equal to a triple integral of the divergence of the vector f. So we're converting to a two-dimensional surface integral into a three-dimensional integration of functions. That's what we're going to do. One benefit here, especially when we volume, this is a three-dimensional region. When the three-dimensional region have a fixed formatting, then the calculation of the divergence causes to reduce level difficulty. So divergence of a vector M. If you remember the definition, the vector's divergence is the tendency of the vector field to go out the region. So the calculation will be the first component differentiate with respect to x, which we get 3x squared, the root of x cubed. So divided by 3, that's x squared. Y squared, then the y squared, I guess. Last component, you differentiate with respect to z, that's z squared. Okay. So to apply the divergence theorem, and then we have to do a triple integral of this function, which is a cylindrical system. The it's a cylindrical coordinate system. I'm thinking about using cylindrical variable, so coordinate. So we will have you see x squared plus z squared equal 4. We were supposed to do a triple integral of x squared plus y squared plus z squared, and then dv of the d. That's the intended calculation. Let me see if you did faster than me. Because I posted a question already at the beginning of the class. I'm guessing some of you might have. Okay, let me open it. If you already have the answer, feel free to put it in. Let me look at what we are calculating. You have to identify this. In our integration region D. This is the integration, and that's the integration function, right? And then based on, remember how we determine the integration variable, which coordinate system are we using? They depend on the integration region. Even though we have x squared plus y squared plus z squared, we're not using spherical coordinate because the integration region is actually a cylinder. So the better coordinate system will be a cylindrical coordinate system. Now, since we have x plus z, x squared plus z squared equal to 4, it's better just do x equal to r cosine theta, y equal to r z equal to r sine theta. We're doing a triple integral, so we can't now change the r to the 4, right? We will reduce number variable. If you do a double integral, you have one variable, then in this cylinder, you only want to keep one variable, then it's two variables. However, what we're doing is among the x variable and z variable, this is a pair variable. This is also a pair variable. So we keep the r, keep the theta. That's among two dimension. That's among the three dimension. That's two dimension. The last variable is y, and you see the boundary for y value. Y is from between 0 and 1, so y will stay as y. So then the original rectangular coordinate x, y, z now become this new set of variable system. That's the y, the r, the z. I guess it could be in the middle, but this is our cylindrical coordinate system. You keep one variable, you see. Cylindrical coordinate system is like the three-dimensional version of the polar coordinate. Coordinate r theta. You also have the rectangle y in this case. Okay, so that's our change of variable. Keep in mind that that's it happening. So we know that the x squared plus z squared is this x squared plus this z squared. So the x squared plus z squared equal to r squared. So it's not the 4. The 4 is on the edge, but the d is a solid region inside the surface. So it's not r. Is not r is between 0 to. So let's try to change our triple integral. We are going to do the theta is equal to 2 pi. It's a full cylinder, and the y is between 0 and 1, and then the r is from. There's a radius 4, right? R squared plus r is the x squared plus z squared. So x and z is on within a circle of radius 2, 0 to 2. I keep forgetting. That 4 is r squared, so r 2. Okay, inside we have x squared plus c squared, that is the r square. The y stayed as y, squared to y, and then we do dy, dr, d theta. Oh, we also have the r, dr, right? This is a linear distance, a distance angle. But for three dimension, you have to three distance measure. So there's one more variable as well. You can make the r in rdr. You can put it together with the r squared, but it won't be in the way before you finish the calculation of the y. Right, so that's the integration limit and the integration function. The rest is calculation. You can focus on calculation on your own, or you can do it together with me. Okay, so let's try to keep in mind the calculation steps. So I have a habit of forgetting the outer layer of the integral, but now let me try to remember that. The inner layer we're integrating is dy. So related to dy, r squared is a function, because of summation, we're not able to get rid of it or bring that outside the integral. So it's going to be in there. So the integration, the outside is u to pi, the outside integral is u to 2. Now let's integrate 0 to 1 for the y, and you have r squared y plus y cubed over 3. It's integrating the y squared. This is the antiderivative of this function, and you have y equal to 0 and y equal to 1. Evaluate at upper limit and lower limit. On the whole side, you still have the rest of the calculation is r, d theta. We don't have to do it until the inner layer is done. Once the inner layer is done, the y equal to 1 will replace all the y value in the formula. So if we finish the inner layer, we're getting r squared plus 1 over 3. Lower limit with y equal to the following 0. So that's what we have. And then we have r, d, r, and then you're going to have 0 to 2 integrated. And remember, the outside is d theta, but d theta won't affect anything of the inner layer. Inner layer is the middle layer is the integration, which will give you a numerical number. So 0 to 2 pi d theta, you're going to get 2 pi. Right, so keep in mind the process of calculation. Let's finish calculating. What if you already have the answer? I have the scanner. Let me see if it's the answer. All the answer that was submitted, they were correct. If you haven't finished yet, anyone already have the number? I mean, I know you guys are faster. So, I'm one of those people that tend to make mistakes and have to think twice and third times before I know for sure. Okay, cool. Thank you.
Yeah, second.
You have. All right. So all the answers that has submitted, they were all correct. If you're still calculating, maybe I'll come back and try to finish. This will be r cubed plus 1 over 3 r, and we compute it and calculate value to integrate to 2. After the integration, we're getting r to the 4 over 4 plus 1 over 3 r squared over 2. And then r is r2 and r with 0 over the evaluation subtraction. If we plug in the 2, is 16 over 4, which is 4. This is 2, that's 4, it's 2, so plus 2 over 3. Okay, and then there is integration on the outside, 0 to 2 pi d theta, which gave us 2 pi. So final answer will be the numbers 3, 12, so 14. So 14 over 3. That's part of the integration. We have to multiply by 2. Okay, so the final answer will be 28 over 3. Okay, I wonder if you're able to follow me. I think that my answer Right. I hope that you all have submitted the answer so far. All the comments submitted. This is one of the question of high divergence theorem. All the question for the first few sections has already been posted. Let's see. Please let me know if you have any questions. Let's try to keep in mind that we are at the end of the semester, so I opened. I think all the chapter 14 were open. The final exam practice will open tomorrow. So by the time next week, we'll have all work open up for practice. And today we'll probably try to cover 14.6, so we don't have too much new material linear next week. So the whole week we'll be practicing questions. Do you have any question with the current homework? It could be any section, any homework. Any questions? All right. If you have no question, let's try to start chapter sections or section 14.6. So the whole chapter 14 is trying to put some connection of all the integral we're doing. So right now, today, this is the last section of the material. We're going to talk about a new, a really fancy theorem. It's called Stokes Theorem. Okay. So the title is called Stokes Theorem and Curl. So as you can see, we'll be talking about how to calculate another thing about a vector field. So the entire chapter 14 have different, almost every section touched on the idea of vector field and how vector field can be applied for, think about vector field as something moved and with relation as something that did not move, like path or curve. Now, Stokes theorem is based on the curl. So we have to know how to calculate curl of the vector. Then we'll be able to talk about Stokes theorem. What is Stokes theorem? Really is a generalization of the Green's theorem. So again, it will be related to line integral. Now, Green's theorem is something. Green's theorem is something we already mentioned. Green's theorem is converted from a line integral into a line integral converted to a double integral. So with Green's theorem, I guess we can write it over here. Green's theorem saying that you have a line integral. This line is a curve in 2 dimensions. You can convert it to a double integral, and again, a 2-dimensional double integral calculation. Okay, so then your curve is within a 2-dimensional plane. It's limited in the plane. Therefore, the double integral is also in that plane. Now we're extending that or generalizing that to 3 dimensions. So we may have 3-dimensional curve. So your 3-dimensional curve are not staying in a single plane. It's not staying in the flat area. 3-dimensional curve could be spiral, and then you can have a surface that is, if you have a closed curve. So this closed curve could be covering some surface here, a surface in the 3-dimensional curve. So we wanted to say if the 2-dimensional Green's theorem can be generalized to a 3-dimensional curve and 3-dimensional surface, that's really the main idea. The main idea of Stokes theorem. So Stokes theorem is a 3-dimensional version of the Green's theorem. Both of them are working on converting from a complicated line integral into a from a line integral into a double integral. Now, if you have 3-dimensional line or 3-dimensional curve, of course, the surface will be a 3-dimensional surface, but we'll be converting it to a surface integral. So let's try to tie a line integral, 3-dimensional line integral, into a surface integral, which will be two-dimensional surface integral calculation. Now, before we can do that, there is something that we need in Stokes theorem. That's the curl of a vector. Let's look at how we calculate curl. The calculation of curl, the definition of curl is defined for a vector field. It's kind of like the name, like how much in the curl, how much the vector field is curling or rotating. So you can see in the calculation, the curl vector, it's a vector field, is also a vector. A curl of vector F is this vector. The first component is dp dy minus dn dz. The second component is dm dz minus dp dx. The second component do not apply anything related to the second one. It's explanation of partial derivative of the vector of the component p and f to get the second of the vector curl. The curl vector's last component is dm dndx minus dmby. That sounds familiar. That's the green theorem. The third component of curl is exactly the same calculation when we were calculating the green theorem. So you can think of a green theorem. The right-sided equation of green theorem is also a curl, but it's a curl in two dimension. Okay, so if you have a two dimensional curl calculation will be 0, 0, and there's that. So there's some difficulty on remembering how curl is being defined. So the top 3 lines are defining the formula for curl, and then the bottom, like the big part, the big half of the whole page, explaining how can we get curl remembered easily. The way to do it is realize the combination of the two can be considered as operator and the second rule of the vector. We use the three-dimensional vector, 3 by 3 matrix to represent the calculation of curl. We put the vector ijk on top, and then this is at least how I remember this. I find this easier to operate, but you should do work it out like this. Okay, so basically, this is a definition for curl. A lot of people find this difficult, even after we learn curl, and we still have calculus, like how you understand what is curl. If you want to understand curl, yesterday we went over this video, which is a video explaining the concept for a vector field. You can calculate divergence, you can calculate curl. What's we represent and what's the meaning, it also shows visual presentation, but feel free to watch that to understand this a little bit better. But let's just look at the calculation. So basically we're looking at writing it into this 3 by 3 matrix. Okay. And a curl calculation, you will need I multiplied by, in this case, you see for I is multiplied by this matrix. Okay. You can think it's not exactly a matrix, it's a combination. So you have this partial to combine with this. So that would be the dp dy. And you have this operator on this end. So the dndz is the same. With matrix, determinant of the matrix, multiply and subtract. So we cross combine and then subtract. So you have dp dy minus dndz. That's for x. That's for I, the first component. All right, and let's look at the second component. The second component is the j. So j, we were hoping it will be also combined with the matrix. However, to me, it's awkward that part of it is on the left part of this, right? In the matrix operation, you cannot multiply an element with element in the same row and same column. So therefore, j would never ever combine with I or k because they're in the same row. J will never be combined with y or n because they're in the same column. So with matrix sense, J will only be combined with this and this. So how do we do it? They also are not going to combine with each other because they're in the same column. So what happens is you're still going to be, the easiest thing to do is roll that over. Roll the first column over so they're right next to this. And that's what I did with cross product. So then you do this. This is a matrix for J. So J will be dp dz minus dp. That was M. All right, so dm dz and dp dx. So that's the component for J. That's the second one. J is the one that was right in the middle. Take a little while to work it out. I also see in the linear algebra classes, people were like this. J is in the first column, second row, first column, second row. So if you add it together and then -1 to this power, make it negative. So you can go negative J, and then you can use this matrix cross and subtract. You end up having dp dx minus dm dn, and there's negatives, you switch. So either way, that also works if you keep in mind the change of sign. But I find it a little bit awkward. It takes time to think straight. So I would prefer to roll around only work with the visible matrix that's in my, like I can see it. There's a dx, dm, dxn, which I roll this one over. You see 1, 2, 3, and then 1, 2, 3, 1, 2, 3. That's what I call rolling the columns so they can meet together. And at least when I was doing the matrix operations, what I handle things that keep changing their signs. So I don't like to have negative, positive alternating sign. So I decided just looking at the rotation. All right, the last one is K. It's easy to tell. K cannot combine with the same column, same row. So K would be a component of this. Okay, so it's d and dx minus d and dy. And that's exactly how we present it when we talk about Green's theorem. That's how we calculate the curl of a vector field. Let's try a question to kind of make sense of it. And whenever I randomly pick up a question in practice, I'm a little bit hesitating about my own choice. I tend to pick up the hardest question, but this one was okay. The question number 1 for problem number 1 is to calculate this. We got this vector F. The first question, calculating the divergence. If you remember 14.5, we define divergence. Divergence is calculating the derivative of every component and add it together. The first component has to be dx. You get a 0. Second thing has to be dy. It's also 0. Last component, so the divergence equal to 0. That means this is incompressible. Now let's calculate the curl. All right, so how do we calculate the curl? That needs to be a matrix form. At least the format looks like easier to follow or easier to track. So it's not easy to do following the method that we're talking about. It is easy to avoid mistakes. So sometimes the method might be time consuming, but if you follow it, you're less likely to have it wrong. It's the reason we choose to do this in such a way. So curl of this vector is equal to student matrix. So we have. So we will write down the IJK that's really indicating the first component, third component, and then we have the partial derivative operator. By itself, they don't have any meaning. We just put it into the right order. Get ready for computation. Lastly, we put all the component of the vector F. In this case, we put in 9YZ and 4XZ and then XY. Those are the 3 components. Now we're going to write it out and vector. So the first, you can also just do this, right? That also works out. So for the I, it's the I, it's this. So we will combine these two. Combine these two. So the first component will be dy of the xy minus the dz of the 4x. Combining it 1 by 1, so more or less kind of like a cross product. You do the cross product in your partial derivative combination. But then under J, I move this move the first column to the right. You can also do it faster, but I'm trying to pace myself so I jump the steps. The second component will be refined and will be dz of 9xd, finding them first. And then we have ddx derivative with respect to x of xy. So that's the second component. The third component is this two. It's okay, right? These two. And we have ddx for xz, and then minus derivative with respect to the y variable 9yz. Now we're done. Those are all three vectors. We write it into vector form. So the first one, you differentiate, we get y. It's derivative of the x equal 1. 1 times y minus derivative of this with respect to z. We have 4x, y minus 4x. Second is 9. 9x derivative is 9. And then there's still y multiplied minus y. The last component is 4z minus 9z, isn't it? Differentiated with respect to x, that's from z to differentiate. Yeah. So that will be negative 5z. Then this will be 8y. For first one, don't see any way to simplify it. X of this. The first component, it was dy, right? It did, it's dy. So it should be x. So it's x minus 4x. So it's negative 3x. Sorry. You can see in indication that I did copy the wrong operator. I copied it was differentiating with respect to y and right x. Same. So the final answer for the is this. It's negative 3x, right? And then 8y. It's kind of interesting that we have a corresponding variable in that component. So we have this into, okay. So this second component is 8y. The last component is negative 5z. The first component is negative 3x. Those are the curl calculation. Hope that gave you some idea. And anything else? The curl of this, the divergence of the curl. The first component, if you differentiate with respect to x, you get negative 3. With respect to y, you have 8, and then 5, you have negative 5. You see what's happening? It would equal to 0. And this is something that we observe that's quite common. And you can try this. Try with any other vector. You calculate the curl, and then you calculate its divergence. They would equal to 0. So it's probably should potential to. Okay, so this is the calculation, practice calculation of the divergence. You think of it as the operator of the dx, ddx, dy, dt, the operator dot f. That's the divergence, which is dot product. If it's a dot product, it's a summation. So in the end, you differentiate and then add. Now the curl is really a cross product. I guess that kind of makes sense. So in this case, you can have the operator with this operator, and have this operator and the original vector cross product. That's the curl. Right, and then you can also, if you don't have the dot or the cross, then it'll be the gradient field. Okay, so this is the concept with the curl that gave us an idea on the computation side of it. So here is a determining the curl of the spin field. This is a 3-dimensional spin, and here are the calculations. Yeah, so it's presented the same way as I was doing earlier. You have all your vectors at the last row of your 3x3 matrix. So essentially, the calculation have that cross product format. So you have a combination of these, right? These give you 1, and this to combine. When the operator with an appropriate function, this will give you -1. This is 1. And then there's a -1. 1 minus -1 is 2. And then for the j, it's these two, but with negative. So these two is -1. Now with positive one, -1 is -2, but it's negative. So it's -2. And so it's minus -2. And for the k is this 2. It's 1. Derivative x with respect to x is 1. Derivative of y with respect to x is -1. 1 minus -1 is 2. Okay, so it's 2 to 2. The divergent, the curl of this vector field, this curl vector is vector 2, 2, 2. So the curl of the spin field about an axis rotation is given by the vector A, this vector in the direction of the axis rotation. So basically, curl measures the spin. Actually, it gives you the axis of rotation, the spin. Okay. Let's talk about the curl of a conservative vector field. We have mentioned before, if we have a function, a two-dimensional function, if it's a conservative vector field, then is according to the Green theorem, d and dx actually and yeah, d and dx minus d and dy we equal to 0. So with Green theorem, we see that a conservative vector field, if you calculate it line interval, the initial point and terminal point are the same. On a closed curve, the line interval equals 0. And Green theorem verified that the curl would also equal to 0. So with that same tone, if you have a function that is a vector that is a potential field. So suppose vector f, it is equal to the derivative of lowercase f. Lowercase f is a potential function. So the first component is df dx, second component is df dy, and third component is df dz. So if that's the case, that's the vector. And curl of the function will be like this. So you have the first component, all the vector component is in the last row, and the middle component is its operator. And we do a cross multiply. See this. So we end up having b by the second derivative df dy dz minus df dz dy. Now it's according to the derivative multivariable differentiation, we see they're the same. I mean, f yd minus f dy is the same, or f dx minus f xz is the same. So these are essentially 0, 0, 0. So the curl will be a vector that has all components equal 0. That is what should be happening for conservative vector field. The curl vector should be 0 vector. Right? So basically, that gives us the idea that a curl describes rotation of the vector field. So then if we have if I have a curl that's not a 0 vector, it will be, if it's not a 0 vector, then it will measure, it will give us the spin, like the axis of rotation spin. So this page basically describes the physical meaning of curl. And the one we were talking about, if it's a conservative vector field, then curl, all three components of the curl equal to 0. Curl basically is a vector for those 0, 0, 0, all three components. And this is the one we called, if the curl equal to 0, then the vector is called e-rotation, meaning the vector is now a fluid that rotates, that make it flow straight in one direction. There's no curling. Any question? If anything that rotate, what I can remember is the screw, like we have a screwdriver and then we have rotation. And we will be able to mention spin. That's the physical meaning of curl. And here let's talk about something that we had talked about in our calculation. Now, if the vector is conservative vector field, obviously curl should be a zero vector. On the other hand, if you have a vector that is already equal to a curl of that vector, then the divergence of this vector that equal to curl would equal to zero. So this is one of the theorem that we already observed in the calculation that we were doing here. Now we were doing question number 1, and the vector had a divergence that equal to zero. But we were able to calculate it. So obviously the curl is not all zero. And then, but if the original function have divergence, but when you calculate the divergence of the curl, it is also equal to zero, right? Even though the partial derivatives are not equal to zero, when you combine them together, this is a persistent result for all vector field. It doesn't matter if it's conservative or not, but if you have a vector that's a curl of any other vector, divergence of the curl equal to zero. This is the result of this theorem. And we can prove it mathematically, but we would not move the theorem is presented here. You can try to calculate it to see how the divergence of it can be calculated. Which related back to the original definition of the curl. So that's our definition of curl. If you try to, so right here are the calculation of the definition of the curl. And you think about if we calculate divergence of this, it will be find the derivative of this function with respect to x, this function with respect to y, this function with respect to z. And you can see a second derivative function of the m and p. All of them are going to be added together. The total summation of all those second derivatives are going to equal to zero. So it's not too hard to the theorem just from the definition standpoint, but we'll take it as granted, knowing that the divergence of the curl vector will equal to zero. Now, this is another example about the curl, determining the curl of a vector, in which every vector is parallel to the x-axis. So the calculation of the curl, this one has only the first component, sum 0. We have z, 0, 0, 0. You can see this 0 in the first component. Second component is 1. The last component, it is also 0. So curl of this vector equal to j. So the vector is parallel to x. The curl is parallel to the y-axis. But the original function is parallel to x. The curl of this vector is in the direction of the y-axis. This is 1 times j. This picture here is showing the vector field. You see the vector is the x component of the vector is equal to the z value. So if you have a point over here, its vector is z going this direction. This is this direction. But if you have something over here, it's going that direction. You get a negative. If it's below, you have negative z value. But it's the x component, so it's a rotation parallel to y-axis. This rotation, if you follow the trend, flow is going this direction, and here it's going that direction. That's what do we mean by the spin is parallel to the y-axis. That's the curve. couple of things about conservative vector field and kind of see what's going on. If we have a conservative vector field, then the curl equal to 0. Also, the line integral of any closed curve is equal to 0. And also, the line integral will be path independent, only depending on the initial point. If it's a conservative vector field, then every should be a partial derivative function. So a line integral at dr only depends on the initial term. So it's path independent paths. These are a couple of questions about conservative vector field in 3 dimensions. All these results, I think, have already been mentioned in green theorem in 14.3 when we talk about dimensional vector field. That's conservative. Okay. This example is trying to determine if this vector is a conservative vector field, and we can find the curl of this vector. Right, and you can see that the curl is not a 0 vector. This is not a conservative vector field. So the answer is no. And this is another example on determining whether the vector is a conservative vector field. We don't have exactly about whether the vector is conservative. See. Is this function a vector field? That's the same thing as saying that this function is conservative. It depends on the calculation of the curl. If the curl of the vector is 0, 0, 0, then yes. And if the curl is not a 0 vector, then no. So when you try to this question, it really depends on the result of the calculation of the curl. For each of the following vector, find its curl, determine if it's a gradient field. Okay, so the answer would be yes or no. Depend on, again, about the curl. So that's pretty much how this is being exercised. So then calculation here, you have to find out all the component and find their partial derivative, and then calculate the curl. Potential function. So this is a conservative field. There's an additional question to it. Once you determine it is a conservative vector field, you also have to find what function is a potential function for the vector field. There's an extra problem. If you want to find if it's already know what this one is a conservative vector field, prove it by calculating on the curl equals 0. So the calculation will involve try to integrate it, right? This is a gradient field, and therefore each one of them is a partial derivative. You have to integrate them one by one in order to determine what will be the function that was a potential function of it. I want to at least talk about the Stokes theorem. So what is the Stokes theorem really? Again, it's the line integral. So you have a line integral basically calculating the flow of a vector field along a path. And that flow, or you can call that calculation of the circulation of the vector field along the path. It's a line integral. So this line integral, we know the difficulty of a line integral, as we mentioned in 14.2. So if it's a 3-dimensional curve, therefore you will have a parametric equation that is 3-dimensional of the curve C. And then this curve might be the boundary of a certain space, certain surface. If the surface is easy enough to classify, we can convert that into a surface integral. Consider a 3-dimensional vector and a surface T. Now, surface T have a boundary that is a curve C. In this, the surface is being bounded by the C. So C has to be a closed curve. Therefore, we have a line integral that's a closed curve calculation, a line integral and closed curve. And therefore, according to Stokes theorem, this line integral equal to a double integral of curl f dot n ds. So it will find out a vector field. It's not the original vector field anymore. It's the curl vector of the vector field. you find out that vector field dot n. N will be the normal vector of the surface that we mentioned in the question. This will allow you to simplify the line integral. It's a three-dimensional line integration into a two-dimensional double integral. That was surface integral calculation. Right, so this is the process here, and the calculation difficulty in the line integral, as we mentioned in 14.2. If you want to calculate line integral is supposed to be a one-dimensional integration. The difficulty is how we describe this line, this curve. You have to determine the formula for the line, and the line will also be affecting how we represent the vector field. If every x, y, z are changed based on the line integral formula. So characteristic or try to understand the line integral really well, and then difficulty in line integral calculation. Now, on the right, if we convert it to a double integral, the problem in this calculation is the same problem that goes with any surface integral problem. As the surface, we have to be able to convert surface integral into a proper double integral. Surface integral are not the same thing as a double integral. ds is not dA. If you remember, ds equal to root of the one. Well, if it's two-dimensional, three-dimensional, the ds should be magnitude of RU cross RV. That's how hard it is to write the ds. But on the other hand, the n is RU cross RV. So n times ds will have n itself has a division of the magnitude, but then ds has a multiplication of the magnitude. These two multiplied, you really could combine that into just a vector itself, dA. So that's a conversion there. Keep in mind that's how we kind of convert from the regular surface to dA. Let's look at an example classes. At least finish one question. Now this question is to use Stokes theorem to calculate the curl f dot n ds if t is part of the unit sphere lying above the xy plane, and f is this vector, three-dimensional vector. So the question is calculating the surface integral with the line integral. Interesting. I guess the lesson that we get from this example is that these two, the surface integral is harder, or the line integral is harder. Whichever is harder, that will be the one we tend to avoid. So we want to pick the easier side. Now let me see if I can finish this question. So we're going to apply Stokes theorem on this results. See. And it's have the formula there, so we can look at it. And over here is a question we try to solve. The question says we want to calculate this, which is what's really on the right side of this equation. Right? If that was easy enough to calculate, we would be calculating the curl of the vector and then calculate dot n that identify the surface. But according to the question, it's also apply Stokes theorem. The reason that we should apply Stokes theorem to calculate it maybe because this side is easier. So we're not, if we are calculating directly, we don't need a Stokes theorem. If we need a Stokes theorem, so that's really the lesson. But I read the question, like, why do we need a Stokes theorem for if everything's already there? So we're going to calculate this instead. Okay, so that's the first part of the first example saying these two, whichever is easier to calculate, and we go by that side. Sometimes this side is easier, sometimes this side is easier. And for this question, I guess this one is easier. We have a surface that we are calculating. It's part of the unit sphere, like above the xy plane. So visually, it will look like this: x, y, z axis, and here is the sphere. We're only looking at the top half of the sphere. It's lying above the xy plane, and therefore this surface has an edge. The edge of the surface is this edge. This edge is at C that we're talking about. So the surface we're looking at is three-dimensional. So we understand that calculating a three-dimensional curve of the surface is not as easy as just calculating the circle. So this C we have is a line. Okay. So how do we represent it? We can just go x equal to r cosine theta is this thing equal to 0. So this part is what we're to r cosine theta. Let's make it easier just to cosine t. And y equals tan t. Remember, a line integral is like one-dimensional integral, so it's not. If we can calculate it, it's not two-dimensional here. So we're calculating just using this. Calculating the t would be from 0 to 2. It's an angle. It was theta. It turned into t. It's easier to make. Right. So we can integrate 0 to 2 pi. Try to convert from the line integral notation to a proper integration. And here we're going to have the f. F was y. And following the line integral cosine cosine y equal to sin t. So we have sin t. And then the x is cosine t. So we have cosine squared t. And then z is the b equal to 0 on the xy plane. B equal to 0. So that's basically 0. So that's our f in this line integral calculation. And a line integral follow the equation of the line. The surface integral follow the equation of the surface, which kind of is making it nice. And then we have to do the PR, which is what was R? R would be cosine t sin t. The vector R is a line and then 0. So this is PR. This is our R. We find R prime, which will be negative sin t. And then cosine t, derivative sine is cosine. Last component is 0, and then dt. So that's how we derive the PR, and then we dot product the two. The dot product between the two will be negative sine squared plus cosine squared. Right, plus cosine squared t dt. And then 0 to 2. Okay, it looks like our time is like that too. And now let's look at the calculation. So basically you derive it into a single integration. So this is a calculation. Okay, I forget to square. I realized that this component. It was a cosine square t, and that was cosine t, so it should be cosine cube t. That was a calculation. So we will calculate both of them. It's a summation. So we calculate sine squares and its derivative and find cosine cube and derivative to have to do a substitution to integrate cosine cube and to our reduction to integrate sine square. The answer for the integration, we have to work out the trig integral, and the answer is negative pi. That's the first example of pi in Stokes theorem. Next time we come back, at least we know some of the concepts for this section. Next week when we come back, we'll try to finish our chapter 4 homework question. In the meantime, you're welcome to look up the final exam practice question. That will be how we follow the actual final exam. That will be interesting. Thank you. See you next week. Thank you.